Welcome back, Eigen people. So, guys, make sure you like, share, comment, subscribe. Check out our website, eigenbros.com. Check out Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and Patreon subscribers. Thank you guys once again for donating and supporting the channel. If you guys would like to also help us support the channel, check out patreon.com/Eigenbros. Me and Juan have been trying to get some more interesting things going, like some good guests. Last podcast we had Jonathan Garrard, so your Patreon support helps that.
It does, it really does. And also for us escaping the capitalist hellhole that is.
Yeah, that's definitely one of the main reasons. So if you have it in your heart, donate $1 and help me and Juan quit our job.
Yeah, if every subscriber on YouTube contributes. Actually, we're up to 5K, right?
I don't think we've hit it yet.
I thought we hit it.
No, we didn't hit it yet.
Oh, we're
close.
4.7. Yeah, we're getting close.
Yeah.
But
yeah, help us out. Let us make content for you guys every day, because we will do it.
We will do it. Don't actually do test us. We'd love to do more deep dives of stuff. It'd be a lot of fun because the episode today we're doing on constructor theory and dissecting that. It's kind of a first look, right?
Yeah, I was really actually afraid to even do this. Juan convinced me to do it the other day. He's like, we should do constructor theory. I was like, okay, I didn't know really what it is, and I was scared though because it sounds like an abstract kind of.
It's a big
deep
topic,
concept, and sure enough, it is one of those.
Here in Oxford, my colleagues David Deutsch and Chiara Maletto, with support from the Templeton World Charity Foundation, are endeavoring to create a new language for physics. This endeavor is called constructor theory.
There are a number of examples that you can think of. One is a law like first law of thermodynamics that says that energy has to be conserved, okay? And this law says that something is impossible, meaning a perpetual motion machine is impossible. And it has a very powerful, very wide reach, because just by stating that, without actually working out trajectories of atoms or specific particles, you can rule out a whole set of phenomena just because if they existed, they would permit a machine of that kind, which is not allowed. And so this is the same logic that is behind constructor theory's laws and principles. So constructor theory, instead of using dynamical laws and trajectories and initial conditions, takes statements about what tasks or transformations are possible and what are impossible and why as fundamental ones. And then it derives explanations about the rest from those statements taken as fundamental. So this is a very powerful switch, and it can achieve a number of very interesting things all in one go, just because you change the mode of explanation.
People who are kind of in deep, let's say, if you're a constructor theory person or someone who works in this kind of realm, I don't know if this will be the most enlightening podcast for you.
Or email us at Eigenbros if you want to come on the show. But you have to be legitimate.
Yeah.
Legitimate,
like you work on it or something, you know, something that the audience would care about. They don't want to know if you're just some fucking Chris Langan who does construction theory in your spare time. I mean, no hate on you, but that's not going to get views.
Please, no hobbyists. We're sorry, but
we still love you though.
We still love you.
Keep doing what you do,
but comment below, I guess, if you are.
Yeah. Anyway, should we try to introduce a little bit what constructor theory even is?
Yeah, let's do it.
Yes, so I guess I found it really interesting what construction theory was, because it's basically they sell it as an alternative way to do physics in some sense, like in the traditional approach to physics. So this is a layman warning, you know, if you're not accustomed to doing physics, this podcast can be a little bit challenging because it's one of these abstraction layer type concepts or subjects. Thank you. Yeah. So we're going to try our best to bring it down to earth if we can, but it may not be as feasible as we would like because it's abstract.
The deepest question is whether it's possible to find a more fundamental mode of explanation for physical reality than the one we already have. Currently, the best you can do if you're a theoretical physicist is usually to find a dynamical law that can be applied to the whole universe, and given the initial conditions of the universe can let you know what the universe will do at some point in the future or in the past. This is a very powerful scheme, so it's been around since Galileo's and Newton's times, but it does not capture some aspects of physical reality that are very important. They require an explanation, they exist out there, but they can't quite be fit into this mold.
Yeah, it's a little bit metaphysical, right? Sort of. It's kind of hard to...
I hate the term metaphysical. David Deutsch even says that as well in one of his things.
He says he hates it?
Or he said better to call it philosophical in some sense.
Well, I mean, that's a subset, but okay.
Yeah. Metaphysics
keep going.
implies something else, though.
Gotcha.
But, yeah, but I guess my point was, what was my point?
Constructor theory is like this...
this heavily abstract thing.
Heavily abstract, yeah.
And the way that we do traditional physics is you solve problems using initial conditions, and then they call it, calculating trajectories.
Yep.
Equations of motion. This is pretty much all of physics is just equations of motion, right?
Yeah, like the modern approach to learning physics is just equations of motion.
Right, and we kind of got that through another heavily abstract subject or concept, called the Lagrangian and Lagrangian mechanics and things like that, and Hamiltonians. These are all related to each other. They're almost the same, not the same, but they're really related. And then also things like Noether's theorem, which is another one of these theorems that classifies like conservation laws and theories. So the more abstract you go, kind of the more deeper and fundamental the insights. And that's kind of the realm that we're in with normal everyday physics of, equations of motion, initial conditions, and this is all mathematical terms if you don't understand that. And this is how you calculate things. To put it really simply, you can think of it like, imagine if you wanted to plot a graph. So a graph like X versus T or position versus time of someone on a roller coaster ride. Let's imagine they're on some roller coaster ride. What's a good ride? Well,
if there's a Six Flags near you in the U.S., I would say the Superman.
The Superman.
Yeah,
I did like that one. That's pretty cool, actually.
Yeah, that is a cool one.
It's the one where you're like floating, right?
Yeah.
So if you're calculating someone's ride on the Superman, let's say the roller coaster, you can calculate their position on the track and plot that as a function on the graph, and you can plot it versus time. So if they're going, let's say it takes them a minute to finish the ride. I don't know if that's long in roller coaster terms because they kind of go by fast. But let's say it takes you a minute to finish the ride. If you plug in any value of time into the equation of motion for your Superman Six Flag ride, you should be able to get back your position on the track at any moment in time. And then if the equations of motion are stronger, which they normally are in physics, we can get the velocity at any moment in time and the acceleration at any moment in time. And this all comes about usually from the Lagrangian, or in quantum mechanics it comes out from the Hamiltonian. And those are two abstract theories that basically produce all the equations of motion. And then you couple that with initial conditions, where initial conditions would be something like, how fast does the Superman ride go initially? Because that one has a boost, doesn't it?
Yeah. But the thing is, I guess the equations of motion, there's only two variables that you need. What is it? Position and
momentum?
Yeah.
For
the Hamiltonian, true? It's X and P, right?
For the Hamiltonian, but if you're of the Lagrangian, then it's all energies, right? It's the kinetic energy and the potential energy.
Yeah, which is position and velocity, I guess.
So I guess it's the same thing.
Sort of, yeah.
Semi-same, right. Momentum change is different, slightly in quantum versus classical, but it's essentially the same thing, right?
Yeah.
Take that with a massive grain of salt when I say the same thing.
So when physicists kind of say, all I need is two things, position and velocity, I guess,
right.
and you're set.
Right.
And those are your initial conditions, I guess, right?
Well, initial conditions, I guess, would be like what would the velocity be initially in the track, or some other things like there's. I mean, you're using initial conditions all day in quantum mechanics, right? When you're solving square well potential problems and things, or well problems, it's like, the particle doesn't exist at this boundary, it does exist, or the potential is infinity at this boundary.
Right.
So these are examples of initial conditions, and those are basically the two ingredients you need to solve any physics problem. You get your equations of motion, and you get your trajectories, or the actual equations.
Yeah. So
constructor theory, long story short, is this new kind of framework for, I guess, solving physics type problems. And to be honest, I really don't even understand how they're doing it, because everything I looked at and read, I didn't actually read any of the major main research
Main
papers.
works, yeah.
I looked at all the kind of ancillary stuff, like the real pop article. Well, not pop, but I guess, yeah, popular articles like
Yeah.
Quanta Magazine. And
Yeah.
I watched an interview with Marcus de Sotoy, and then also some things with David Deutsch,
Straight from the
guy who
horse's
created
mouth.
Constructor Theory. Yeah.
Yeah.
And they kind of didn't really describe it in any kind of real tangible way. So what I can tell you is kind of like the abstract version and try to bring it down as much as I can.
Yeah, so for the listeners, I'm going to give them what Wikipedia says,
Yeah.
and then we can expand on it. So
Sounds good.
it says here, constructor theory is a proposal for a new mode of explanation in fundamental physics in the language of ergodic theory.
Oh, boy.
Ergodic theory, who knows what that is? No, I'm just kidding. It's a branch of mathematics that studies.
Ergot, isn't that a League of Legends character?
Well, it's a branch of math that studies statistical properties of deterministic dynamic systems. But yeah, that's a whole subject that you can look into. But it was first proposed by David Deutsch at the University of Oxford in like almost 10 years ago, 2012. And it expresses physical laws exclusively in terms of physical transformations or tasks, or which tasks are possible versus which are impossible and why. So they allow such quote-unquote counterfactual statements into fundamental physics. It allows new physical laws to be expressed, such as constructor theory of information.
Right, so let's break that down a little bit.
Yeah.
The key takeaway I would take from this constructor theory is, if you're asking, like, what is the point of constructor theory? What does it seek to do? The main answer to that is it gives you a binary choice of, or I guess it gives you a dichotomy of relations. It shows you what can be possible and what is not possible with a particular system that has a transformation applied to it. Long story short. So it's almost like not a normal physical theory you would think in terms of, traditional physics, which is why they call it this new way of thinking in physics. It's because, yeah, they're trying to do, I guess, different things than what we might normally do in physics. But this isn't anything too strange, right? Because we kind of do this with, like, Gedanken experiments and
Exactly,
sense, right?
yeah. Well, yeah, that's kind of the genius, actually, of this,
Right.
because of, admittedly, I listened to the audiobook by Chiara Marletto, The Science of Can and Cannot. And she's also one of these other leading contributors to this theory.
Yeah.
But you brought up the fact, like, okay, there are Gedanken experiments, and there's a statement that they use in the Wikipedia article. It's called counterfactual.
Yeah. That's one of these
statements.
reserved words in the constructor theory lexicon.
Mm-hmm. Yeah, and it's kind of it's kind of hard to describe. Like, if I look up the definition, it's a little bit. I mean, some people might be like, "What does that mean?"
Well, I kind of found an example of a counterfactual, just not even related to constructor theory, because I think they borrowed the term and it means maybe the same thing. We can clarify this. So put an asterisk on this part of the podcast. Sure. I think it is, though. But from what I found, it was like, it's basically a conditional statement.
Right.
Only it's got a negation involved. So, for example, the one I guess the basic or the root structure of it is, if not X implies not Y. Or I guess if you want to inverse that for the cause and the effect, it would be if not Y, or if not Y implies not X. So you can fill that in by saying, for example, they used this one on Google that I found was, if I had not burned myself with the coffee, which would be Y, that's the effect. I'm sorry.
If I threw the baby out with the bathwater.
Okay, you're making a new.
Not making a new. No, but it's
I wish I remembered it. Now I forgot.
Well, we can definitely if you Google it, please insert it so the video watchers will get a little quote here. But I want to give like a definition that I thought was a little more elucidating. It says it's an adjective expressing what has not happened but could, would, or might under differing conditions. And that is a counterfactual statement. So, for instance, a counterfactual statement would be an expression, or counterfactual thinking is what is possible and what isn't.
I think I remember my example.
Sure.
It was if if I had not burned myself, this implies that I did not make coffee.
Oh, I see.
That was the counterfactual statement.
Uh-huh.
I don't know if it applies squarely with constructor theory, but
Yeah.
I think when I read it, I was assuming it did.
It's built on. I mean, the whole construct of it is built on the language of counterfactuals. It's like, I mean, the example that Chiara gives in the book, or she gives multiple examples actually. She says, you know, a good example of this is the conservation laws. The conservation of energy is a big counterfactual because it constrains you in a lot of ways. And in fact, a good example, a recent example of counterfactual thinking was the neutrino observation that led us to discover something as opposed to dynamical equations. Because some people argue that dynamical equations, like things fall out. There are good examples of like in history of like, well, the equations of motion would tell us that this is going to happen, right?
Well, that's how it's always been done, right? I mean, we've gotten all our knowledge from that pretty much.
Counterfactual thinking or
No,
dynamical
from
equations?
Dynamical equations, kinematics, because this is the framework of physics, right? Like people, when you think of physics, you think of, okay, I'm going to make some kind of a few axioms about some system or something, or use some experimental data to create these axioms for this system, and then I'm just going to follow the logic from these equations, and your theory gets built up from there.
Well, I think their argument would be that that's a lot of big scientific discoveries were. I mean, she kind of argues in the book. I've only gone, by the way, 4 chapters into the book, or 3 chapters into the book. So
this is definitely an introduction.
Yeah. So, but I've gotten enough of the foundation to really kind of like parse through some of the nuances here. But she argues that Einstein kind of thought in this counterfactual framework to come to relativity.
Yeah.
Yeah.
I think this counterfactual framework, it's been given a name now.
Yeah.
But I think many of the major, at least especially the intuitive type scientists, already kind of use this in an informal kind of way.
Right, yeah.
You know, like Schrodinger's famous example, the Schrodinger cat. I guess you could call it a counterfactual, or the Maxwell's demon. You know, these classic kind of thought experiments. I'm not entirely sure exactly what it means by why they are counterfactuals, because that's just a thought experiment to me. Like, what makes them a counterfactual specifically?
Yeah, let's dissect that because of she brought it up, and I wanted to see what that really means, because counterfactuals are supposed to be what is possible and what isn't. So, like for Einstein, it would be like,
is that what it is?
Yeah, essentially.
Because it's different from the definition than on Google of a counterfactual. There's just like a conditional statement.
Right, but I guess a
conditional
version of this would be like if Einstein said, "Well, the speed of light is this," like okay, so if we're moving, okay, here's the Gedanken experiment.
Yeah.
Do you remember it? Like, do you know it like the back of your hand?
No. The one with the train and the lightning? Yeah. No, hell no. With relativity, I don't know anything like the back of my hand. Like, I always have to take like 10, 20 minutes to just think about it first.
Well, we always talk about this, and this is like such a famous one, but he's on a train. He watches lightning strike or something, and no.
Well, it didn't actually happen. But
okay.
It's irrelevant to the story. Go ahead. No, Einstein's train did not get struck by lightning twice at the same time.
Well, essentially, he sees lightning strike or something, and then he thinks about if the speed of light is constant or something, or he plays around with this idea.
Yeah, he thinks about what would happen if the speed of light was constant.
Yeah.
If lightning struck his plane from 2 different sections.
Right.
Because one of the consequences he gets from relativity is that, time is relative, right? So time depends on your frame of reference. So then he was just thinking, like, what the hell would that look like in real life if the lightning struck the front of my train and the back of my train at the same time, quote unquote. But you can actually see from, I guess, long story short, like, relative to the observer, the lightning strikes at different times for some observers, and it strikes at the same time for another observer, and it shows you the relativity, I guess, that comes out of setting the speed of light to be constant for light.
And I think, but I guess in that explanation that you gave, I think that is an example of a counterfactual statement, because it's quote unquote from the definition that I pulled up, it's an expression of what has not happened but could.
I see. So
yeah.
that's the kind of the counterfactual part of it. Like,
Yeah.
I don't know if I necessarily like the name.
It's a little bit. It's kind. That's what I'm saying. It's a little weird to
Yeah.
kind of wrap your head around because you're.
I don't like really any of the naming the constructor theory. I got to be honest. I don't know if it just has to
The
grow on me.
language.
Yeah, the naming scheme is not great to me. Like, I don't like the name constructor. I don't like the name counterfactual. Because I mean, they're like, for one, constructor I already know from computer science, right? Constructor is an object-oriented term. Where it's like it's a subroutine that creates objects. So I guess kind of like a constructor, but it's not the same in this one. And then counterfactual is like a negation of a.
It's a borrowed term too from. It's a pre-existing term.
Which one?
From counterfactual.
Yeah,
Yeah,
that's what I'm saying. It's a logical. It's a logic term, meaning a conditional statement that has a negation quality to it. So yeah, I'm a little bit confused by the terminology. I don't know if it's just because I haven't wrapped my head around it and I'm just being stupid, or if it's literally just being used in a kind of strange way.
I mean, I had trouble with it too, just from reading the book or listening to the book.
Yeah.
But they give enough examples in the book to kind of, for me to really grasp what they're trying to say. And but they were saying, like, the most recent example of this kind of thinking is they argue that we need a paradigm shift, and this is the kind of paradigm shift that's going to elucidate a lot of interesting things that we have not figured out in physics yet. So, for instance, like going back to the neutrino example, you weren't able, or physicists weren't able to figure out from dynamical equations that the missing neutrino, what is it, mass?
The sterile neutrino. So there's
is it the sterile neutrino?
There's a.
Sorry, I'm
sorry. You're talking about the discovery of the neutrino.
I think, yeah.
Pretty
I think
sure
this was like a more recent thing too, but
it's not
what's
recent.
from experimental data?
Oh yeah, I guess it is kind of recent, huh?
Was it 2016?
Yeah, you might be right, because people were debating on whether neutrino even had mass, right?
Right. But anyway, she argues that, or they argue, particularly she, I think, the neutrino data that they came up with, they approached it from a conservation of energy point of view, not from a dynamical equation thing.
Right.
So really, they use counterfactual thinking, like, well, there's something missing here, but we know conservation of energy says that there has to be something here.
Right.
Yeah.
And the specific example of that would be in particle production, right?
Yeah.
They knew that there were these collisions that would happen. And of course, for conservation of energy, you know, and also with particle physics, you can have a particle that has a certain energy, right? And then let's say it decays into a couple particles. So let's say they saw one particle decay into two particles, and then they added up the energies, and the energies didn't add up. So then they said there's missing energy here. But we know from the laws of physics, and basically an axiom of the universe that we take, you know, we take it for granted pretty much in physics, is the conservation of energy, that all energy is created or cannot be created or destroyed. It can only be converted into mass and energy. Mass energy can be converted, and that's it. So then they just posited that, okay, if there's missing energy in our calculation, that must mean that some other particle we cannot detect must exist.
Yeah.
And sure enough, that was part of the discovery of the neutrino.
Yeah.
Because it did have that, I guess what she's calling it, a counterfactual quality. I don't really know if I like that, but, you know, because to me, it's just, that's just how you reason in science, right? But I guess...
But they're arguing for a paradigm shift. This whole thing is like...
Well, what I guess I'm taking away from this, rather than maybe a paradigm shift, is more so, it sounds to me kind of like they're formalizing the thought experiment in some sense. Like you're taking thought experiments and making them formatted in such a way where you can actually utilize them. Like, it's like if you were doing physics problems, you would take a formalized approach to also doing a thought experiment alongside it in a formal way. That sounds like a very powerful thing to me.
Yeah.
Honestly. And I mean, it kind of reminds me a lot of Gödel's incompleteness theorem too, because Gödel's incompleteness theorem is this theorem that tells you about, you know, what I guess proofs are possible in mathematics. And, you know, people have always taken the approach like, oh, we can do like, what's it called? They do all these different processes for proof, and they also have a form of negation in proofs where it's like you proof by Was it
I
called
know what you're talking about.
counterexample?
Counterexample, yeah.
Something like that, where they can actually prove like things can't exist. I don't know if that's exactly right, but they can prove things can't exist by showing that it's paradoxical or something
Exactly,
within
yeah.
the proof. And Gödel's incompleteness theorem is like this interesting formalized approach to actually making it so you can show if your proof is actually even provable in reality. So you can do this weird symbol symbol
Symbolic,
manipulation
yeah.
in Gödel's incompleteness, where you can show that, oh, this is actually provable or this is not provable. So it actually shows that some things cannot be proven.
Mm-hmm.
And this counterfactual thing, in that sense, kind of reminds me of it's like a framework of thinking about things that they've already done, but it's like adding a formalized approach to it in some sense.
Right. Yeah, because I mean, what was interesting in the book that I had never really conceptualized fully was that right now we have a hybrid model in the way we learn it. She's saying that we have, in some ways, when we're approached these conservation of energy rules, but we use conservation of energy rules or the principle to kind of guide us in the dark sometimes.
Right.
But then in other frameworks, we purely rely on dynamical equations and initial conditions. Mm-hmm. But the contemporary prevailing school of, I guess, doing physics is all about predictability and what would you call it? Determinism, I guess, like in some way.
It's careful.
Well, predicting the motion of an
quantum
object.
mechanics does exist.
I know, but this is kind of, but that's, yeah, I see what you mean.
Yeah.
And
Determinism's a loaded word.
And we'll get to that.
Careful.
We'll get to that because she was saying that there's a lot of, if you think about dynamical equations, they don't really capture the complete picture of physics.
Yeah.
But we can dissect that more.
Mm-hmm.
But what was interesting to me though was that they brought up something, or she brought up something that was called that I guess could be characterized as anti-reductionism. So most of physics is, we're trying to get to the most basic constituent parts.
Mm-hmm.
And then
most of Western things always been that, though, in some sense.
Yeah, sure. Can you expand on that?
Well, you could just think of it from all the way from the conceptions of Western philosophy, right? Mm-hmm. You can contrast it with Eastern philosophy, where they're more about collectivism and always have kind of this holistic approach to things. Mm-hmm. From Buddhism and Confucius and even like some of the Middle East kind of philosophers.
Yeah.
I forget their names. But Western thinking has always been very reductionist in thinking. It's like philosophy from the beginning.
Yeah.
Socrates, Plato, even all the way to the modern era. When you have Nietzsche and all these guys, it's always reductionist thinking, and then you can evolve that into physics even.
Yeah.
But I'm curious, why did she say this is not reductionist?
Yeah. So hold on. Let me pull this up.
Yeah.
So I want to hear your take on this.
Throwing his phone down.
No, I want to hear your take on this. But this is a reading from The Science of Can and Cannot, and we're going to go ahead and listen to this and talk about it. This is chapter 1.
All right.
And here we go.
It confines physics only to things that can be described exactly in terms of statements about what happens given the initial conditions and laws of motion, but not about other phenomena, which thus remain only imperfectly explained. There is more. The traditional conception of physics has inspired an approach that has now spread to other parts of science too, via an approach that has been called reductionism. The idea that there is only one level of explanation that is both fundamental and admissible, and everything else can be reduced to that. Such a level of explanation is, presumably, that of elementary particles or fields and their trajectories, given their initial conditions. But this take on physical reality is again too narrow. There are questions that this approach cannot answer, questions that are deep and important for understanding the full reality of a physical phenomenon. For instance, the question, why is a given transistor in a computer on at the end of a given computation, has at least 2 answers. One is that it is on because the electrons in the computer were set in such and such initial conditions. The other is that it is on because the computer performed a computation to find the factors of, say, the number 15, and the on transistor is part of the encoding of the output, 3 and 5. A reductionist would discard the latter explanation as less fundamental, because, after all, factoring a number is nothing but electric currents in the computer. Reductionism ultimately denies that the computational description is necessary, though some reductionists may accept that it is helpful as a manner of discourse. But this, of course, is nonsense. Both explanations are essential to understand what is happening. They refer to different, autonomous levels of explanation, which do not implicate one another.
All right.
Your shit hurts my brain.
So did you gather what she said?
Not really. It's bordering on philosophy for me, where it's like I don't know what the hell she's talking about right now.
So she was okay. So for the listeners, because it's rather monotone, to be honest. But the synthesis of the argument is that, a reductionist would look at.
I kind of need a definition of reductionism, and also maybe I guess I gotta understand what
reductionism.
What is reductionist
I think
saying?
in this context is more about like materialistic, like saying like, okay, the electrons, like in the first example, she was just saying like the reductionist would look at why a transistor was turned off from an on state. It would just be because.
But it almost sounds like she's just saying someone who maybe favors just analyzing the material properties versus maybe the underlying conceptual part, which isn't necessarily reductionist in my mind. I don't know. I'm a little bit confused.
Yeah,
I think I might have to.
Hold on, elaborate though, because we can.
I don't know, because it just sounds like it's like someone. I don't know if I don't know. This is one of these things where this is why this stuff needs way more examples to me.
Yeah.
I said this to you earlier before the podcast. Is like with heavily abstract theories, I think people make the mistake of not heavily inundating the audience with examples.
Oh, then the book they do give a number of examples. This is just
I need way more examples. You know what I mean? I'm talking like 3, 4, 5 examples, because when you're talking like this in this very abstract philosophical way, I almost have to like take 30 minutes of my time just decoding every single piece of their sentence, because words a lot of time don't do this kind of stuff justice.
No,
the linguistics and words are always will fuck you up. Like we already know this. Our audience knows my gripes with quantum mechanics. People saying that a state can be in 0 and 1 the same time, and trying to explain like measurement superposition as consciously observing the particle. It's all this stuff is fucking your mind up, because it's an abstract layer of, we're describing these things in an abstract layer that doesn't really square one-to-one with our language, and it just winds up being way harder to decode things than just knowing the mathematical framework or something like this, or giving multiple examples. And it's like wasted breath. It's almost like I can't understand unless I really mull this over. So I don't even know if I'll be able to answer
the irony is that she would agree with you.
Okay.
Yeah.
I mean, I don't see any irony there, but I'm just curious why she would take this approach, though.
Well, the thing is, in this particular example, I'm going to try to like explain it to the audience, because they might also be left scratching their head. And I think like, so to reiterate the point, she's saying like a reductionist, mostly I think in the context of being a materialist, would be like, okay, I can explain to you why the transistor turned off, just because the electrons are it's the way the electrons are programmed to just turn off, right? Yeah. They accumulated here, and then this is what happens in a p-n junction.
Sure.
And that's why it's an off state.
Sure.
But she's saying no, that's also missing this other layer of information that's actually critically important to explain why in a bigger sense. It has to do with the fact that the program asked for the transistor to hold on to stay on in the on state, because it's waiting for the calculation. Like, you know what I mean?
Right. It just sounds like someone who's like takes things literal versus someone who, who is actually thinking on a conceptual level. So it's like, I don't know where the reductionism necessarily comes in there.
The
it's
reductionist,
not really the right word to me.
I
don't know. I'm not really
what you
feeling
mean.
it.
I see what you mean.
Yeah.
So your gripe is with like the fact that, I guess in this context it would be a materialist. I think she's kind of.
Yeah, I just wish people would not talk so. I don't know.
Loosey-goosey?
Yeah, so like philosophically. That's, it's like we're physicists. You got to get past that philosophical speak. I mean, of course I understand, especially abstract layer stuff, because like I was saying again, it's like this stuff really always sucks to talk about linguistically. But it's like, if that's the case, to me, I would just give more examples rather than trying to talk about this specific thing, because I'm getting stuck on these words and things, and I'm not really understanding what she's saying.
Gotcha. Okay, so I think another good example would be, let me see. I think she gives an example of like colors or something, but
Okay. I'll just comment on this
Sure.
stuff. I mean, I'm getting really the sense of this theory. Like, I don't really understand even like how this is useful yet, because
we're about
like,
to get to that.
I understand like what she's trying to do, and what David and Kiara are trying to do here, but like I think maybe their approach is wrong. But maybe this is also not for me. Maybe the audience is more for laymen or people who are just trying to get a general understanding of things, who doesn't necessarily care about accuracy or precision or trying to really understand deeply. But for me, I just don't like this approach, because it's just almost like philosophy in my eyes. It's almost like I don't know, like philosophy, I don't know what the fuck they're ever talking about, because they're just using all these reserved words and new definitions of things and all these strange vocabulary for things that they're so caught up in their own definitions. You have to really understand what the hell they're talking about.
Damn it! Hold on. Why did it do that? Okay, sorry.
Yeah, but what was I saying?
They get caught up in
they get caught up in this terminology and things where they understand the meaning, and then when they're writing it, it just becomes a convoluted mess of not understanding. So for this, I mean, I would just try to keep it as real, down to earth, and simple as possible. And I guess it's me. I always have this gripe with any kind of abstract theory, so maybe it's just me. But I think that's just the best approach to do abstraction. You got to bring it to reality.
Yeah.
Because abstract stuff, the only way you're going to really have power in abstraction when you're talking about it, quote unquote, is if you're talking with math. Talk with your math if you're going to talk abstraction. Yeah. Otherwise, just give me a shitload of examples, because I don't know what you're talking about.
Yeah, and I think they do get into that kind of work later on, because it is a theory that is being like presently constructed. It's still not fully fleshed out, I think.
I wish they would also give me more examples of the formalization, because like I was saying earlier, this seems like it's like almost a formalizing of thought experiments, right?
Well,
I wish they would show the formal structure of it. Maybe they do in the papers. I haven't looked at them.
Yeah. The papers, I think, flesh out more of the kind of axiomatic framework of thinking that they do. And in fact, I'll go later on in this, we'll touch on some of the more how this abstraction is tied into physics. And that is a point that she tries to make. So maybe we should have also explained the credentials of the people trying to do this. I mean, David Deutsch he's a quantum
he's a household name. Like,
yeah, well,
I've heard the name David Deutsch. I don't even know who he is really, but I know the name.
I know, I've heard the name before too, and I didn't even know who it was. But he's a quantum information guy. We did a video on quantum information stuff a couple months ago. I don't know what that
We've done a
is.
couple of videos, I think.
Yeah, and his name has come up multiple times because he's such a prominent figure in quantum information stuff and quantum computing. But he decided to tackle this, and then
it makes sense too, because physicists, especially in the quantum realm, are obsessed with information right now. It's like the leading edge right now of physics is like people are stuck on information and trying to understand what the fuck is information.
What does the existence of information tell us about the laws of physics? Well, in constructor theory, we can answer this question exactly in what we call the constructor theory of information. And with that theory, we bring information directly into fundamental physics.
And we'll get into that too because of the thing is Chiara Marletto is her name. She's also at the University of Oxford, and she's a theoretical physicist.
So my background is in quantum computing, which is a theory that was proposed a while ago to use the effects of quantum theory to power computing machines. Out of this field of quantum computing came a number of new proposals to take the laws of physics forward from where they are now. And one of them is this thing called Constructor Theory, which is the theory that I'm working on at the moment.
So she's kind of working with him. She saw some of his initial work and was like, I want to jump on this.
Right.
This is the wave.
Right.
So
she thinks it's the wave.
She thinks it's a wave.
Yeah.
And I agree. But I think this is where the field is going. It's going to more. It's trying to find different ways of thinking about physics to try to get to new, new physics. I mean,
yeah, you're right.
Because we're hitting walls, right?
Right, because just with this last, I guess, for example, with the sterile neutrino announcement, I saw one article, or I saw an article, I don't remember who said it, but they were like, we're satisfied because we didn't get the result we thought. It just shows you the starvation that these theoretical, especially these theoretical particle physicists have. Yeah. We're just like, we don't understand anything new. Like, we just keep getting what we want out of all these experiments, and it doesn't tell you anything new about physics. And we're clearly at a roadblock, right? Because we don't know how to unify gravity with any of the other forces. And, there's a bunch of holes still within, the fundamental theory of physics trying to align and unify everything. So physicists are kind of at their, at the end of their line. They're just trying to think of anything now. They're like, it's in the theory of everything department. They're just like, what else is there to know?
Yeah, but she argues that, in the time of physics that was the most constructive was the time when there were a lot of physicists doing counterfactual thinking.
I see.
Yeah.
So I'm not sure I agree with that.
We need to like she was saying, like Einstein, general relativity wouldn't have really become as popular as it is if there wasn't somebody that thought like that. And
but you could argue, like, think about Newton's days. I don't know if he was really.
But funny enough, she actually brings that up as a fact, as an example of counterfactual thinking.
Oh, really?
Because Newton's 3 laws are about what are possible and what isn't.
Oh, I see. So she still considers that as well.
Yeah.
Okay. Fair enough.
So a lot of these really strong concepts that take us very far, up until a certain point, obviously, for some of these things. But they get us far enough to where it's like you see limitations sometimes, right? Like Newton's laws break down at certain regimes, but they helped us get to those boundaries, right?
Right, right. But I wonder, my retort to that would be, is that just because there was so much undiscovered physics? Because if you really think about it, Newton was the conception of physics, right? Which is the classical realm. So it's rife with everything, right?
Yeah.
And of course it's going to be productive because it's literally the beginning of physics.
Yeah.
And then Einstein, you could argue, is, okay, we're now exploring extremes. We're exploring what happens when things are going extremely fast, when things are extremely large.
Yeah.
It's bound to happen, right? It's completely unexplored. And then you can think of quantum mechanics with Schrodinger in them. Yeah. It's like, because now we're dealing with things that are extremely small. It's extremes once again. So now we've covered all the extreme ends. What else is there?
Well, the funny thing is that she argues she's like, because you're saying that's low-hanging fruit, but she says there's no such thing.
Well, low-hanging fruit, I have a little bit of a gripe with that term, you know what I mean? But I'm saying it had to be, it almost feels like it had to be discovered in some sense, because it's like we're starting at the normal stuff.
Yeah.
Let's let's crank up all that normal stuff, go to high energies and fast speeds, and now let's crank it up another way where we're going extremely small. It almost feels obvious in some sense. Yeah. Quote unquote obvious.
It might be retrospective thinking, though.
I don't think it is. I think it's just like we know we have to go in these areas eventually. Now it's like, where the fuck do we go?
Information,
almost.
Bro.
Yeah, but that's more abstract to me. It seems more like an abstraction.
I think that's a good segue to well, I guess there's a second point I wanted to make, but it's a little bit let's get into the bread and butter here.
All right.
No, you know what? We're going to go ahead and try hitting the second point that I wanted to gloss over, but I think it's kind of important because it ties into what we were discussing a little bit earlier.
Let's do it.
There's a segment in the book that she was saying dynamical equations based on initial conditions are insufficient and suffer from infinite regression.
I don't know what that means.
So like,
Can't she just speak normally?
come on, theoretical physicists, come on. Yeah, 'cause see that's the language. Their language is very.
I'm such a what do you call it? A hater against philosophers. The closer you are to getting philosophy, it's gonna annoy me.
Well, regression. It's like recursion. It's like she argues that like when, for instance, she gives the argument of the Big Bang.
Okay.
Where it's like you would argue, you know, a pure physicist in today's tradition would be like, well, I can tell you everything that comes after the Big Bang if you give me initial conditions, and
sure.
And what else? Yeah, initial conditions, right?
Sure, yeah. And maybe just the equations of motion.
And the equations of motion, yeah. If you were to give me that, I could plot everything up to the end of time.
Yeah.
And so and she argues that, well, that's kind of silly, because it doesn't take into account even aspects of like what came before the Big Bang, like, you know, things like that. Like there's certain things that are just seem kind of give you more questions than answers.
I see what you're saying. Maybe not that example you used specifically before the Big Bang is a bad example, I think.
Yeah.
But I think I know what you're saying. Like I've always had this kind of thought myself because it actually was spurned for me when someone said one of our teachers, I believe, said like electrodynamics is a complete theory. Mm-hmm. And I was like, is it really a complete theory? I was thinking about that. I was like, how do you know when a theory is complete? And I was like, I guess it kind of is in some sense because we know Maxwell's equations, right? You know, you just plug in Maxwell's equations. You should literally be able to do almost everything with that. But then I was thinking, I was like, it doesn't feel complete though to me. It's like, can I answer literally everything I wanted to answer about electrodynamics if it's a complete theory? And I was just thinking of things, and I always come up with different questions I still have. It's like, you know, like, can I somehow derive like what light is from electrodynamics? And then some person might say, well, you can if you can separate the electric field from the magnetic field and using a gauge transformation in Maxwell's equations, right?
Yeah.
And it's like, does that really tell you, like, are you really deriving light though? Mm-hmm. I wonder. Yeah. Like, how would you know it's light necessarily? And I guess you kind of can because you can get the equations of motion, right? Mm-hmm. For the fields, but I don't know. I just always have the thought: is it complete? And I think Chiara's kind of answer is in the right direction to me. Like, it doesn't feel like it's complete yet. It feels like there's more. Like, when I feel like something's complete is when I can answer everything about it.
Yeah.
Right? Yeah. From first principles. And I don't know if I still feel that, even with electrodynamics.
Yeah, and she makes that point too. And later on in the book they get more into it, but that general sense of because physics is mostly a theory about accuracy, right? It's like how accurate something is.
That's a part of it.
You know what I mean?
For
like,
sure.
I mean, like she was like, I wouldn't dare say, just because it's accurate doesn't mean it's true, for the most part, because it can be, like, for instance, Newton's
like curve fitting. You mean?
Yeah, like Newton's,
Sure.
Curve fitting's probably a better example of this. Just because you modeled it doesn't mean that equation is what.
Right.
This is. That's the reality.
Like you're just modeling every single point to match exactly.
Yeah.
I mean, that's not saying that you did a good job of modeling it, right?
Yeah. I mean, the argument is that she's looking for something more fundamental, and she's trying to go to the counterfactual constituents, which, interestingly enough, she based on with David Deutsch's collaboration. It's on physics. I mean, it's on information. She gives an example of information and how it ties into physics.
The traditional way of explaining physics can talk about information in ways that are approximative and not very exact, but can't quite capture the laws that underlie information itself. So I think this was one of the the key motives behind the, proposing constructor theory. Information is very different from anything else we have in fundamental physics. It's not an observable, it's not like the velocity or the charge of a particle, and it somehow transcends the physical systems that contain it. Just think of a message, for example. It can be embodied in the transistors within a computer. It can be spoken aloud in vibrating molecules of air, and it can even be instantiated in the flags of an air traffic controller. And yet, the meaning of the message stays the same. If information transcends physical systems, how can that be a physical theory of information?
And she's defining an information system as any system containing information can be set to one of binary states, like 1 into 0 and vice versa. And then the second property is information states can be processed, meaning they can be replicated, translated, that kind of thing. Mm-hmm. And that's what constitutes information that has, or a system that has information. Because you're arguing for, in this whole process, you're arguing for like explaining reality, right? You're trying to say like, well, you do have constituent particles, but then you do have all this other phenomena that is replicate systems. Like for instance, like life, right? Life is probably the most clear example of a replicating, self-sustaining system that's based off physical laws, right? Mm-hmm. Like there's another layer, like, yeah, you do have the materialistic aspect, the reductionist part, right? Where it's like, okay, yeah, you've heard the statement, right? Like, oh, emotions are just chemicals or something, right?
Chemicals in the brain or something.
But it's, I mean, we all know, yeah, I mean, if you're looking at a reductionist view, yeah, it is.
Yeah.
But we know it's not that trivial either. There's another layer there.
Yeah.
Where it's like you have more going on than just chemicals in a soup. Like, you know what I mean?
Right,
like,
right.
Yeah.
It's oversimplifying, maybe.
Yeah. Do you know what I mean? Like,
or maybe it's just not providing an enlightening picture
it's
for a problem you're trying to solve.
That's a good example of like, that's too reductionist of thinking.
Yeah, right? I guess, I hate the word reductionist, but I guess maybe it is too reductionist. It just really depends on the problems you're trying to solve, right?
I mean, if you're trying to solve the problem of consciousness,
problem-dependent.
Like that's a good example of like, that's too reductionist.
Yeah, sure.
Yeah. Right? I mean, I think their argument is that you would need another layer of information, and here, the interesting thing is, I guess trying to define information systems. Mm-hmm. So, just summarizing it, they're saying an information system is something that has binary states, 1, 0, on, off, anything like that, anything that you can discern like that. And then the second property is that it can be replicated, translated, etc.
Yeah.
Like,
okay.
You can form a transformation.
So what's the point of all this then?
So they're saying information is they argue that information is a physical thing, or can be seen as a physical property.
Yeah.
Because physical systems allow these kinds of counterfactual systems. And they argue that the informational systems are counterfactual because they're conditional. Meaning if something can have an on or off state, right? Like a good example of that we have today is like spins, right?
Sure.
That's a good example of like something that can be counterfactual or can store information.
I hate the word counterfactual.
Yeah,
I just don't understand what it means.
Dude, it threw me off because I had to look at the example. Like I was driving most of the time, so I was like I had to pull over and park and be like, I gotta Google this again. Does this mean?
Yeah,
this?
I keep like reading it, and then I think I might understand it. Then I look at it later, and I'm just like, what the fuck? What does this mean? I don't like this terminology, man.
Because factual, they gotta change it up.
She gotta really fix this
y'all
stuff.
You and David Deutsch and
Kiara
have to come together.
That's the Eigenbros gripe. What the fuck is the terminology? That's my main gripe. Unless they can really convince me it's extremely useful. But
yeah,
right now I'm hating the word counterfactual.
No, because the thing is, when I think of
factual and
factual,
whatnot,
if you're saying counterfact,
yeah, it's just like why counter? Why counterfactual?
Why countering? Why are you countering the fact?
Yeah, it's like why does the counter need to be there, and I don't know. I don't like it.
Yeah, because
can
I mean,
we try to do without it? Let's try to do without it as much as possible because I don't like that
Gotcha.
term.
Okay, well, they're saying that information is a physical property, they argue, because physical systems can actually allow for these kinds of systems to persist.
Okay. I see you trying to go around it.
I am.
If it's too tough, then
No, it's
by all
fine.
means,
These kind of conditional, how about that? Conditional systems.
yeah, but I wonder if we're substituting in that properly because that's
Maybe.
like, why not just use the word conditional then? It just seems so much easier than counterfactual.
Maybe you're right. Let's not do it.
This is why I was afraid of doing that. It's like I don't know. I can't understand it.
Well, the interesting thing is she starts discerning what kinds of information systems like are perpetuated in this universe, right?
All right.
Like whether or not because it really just depends whether or not information is permitted depends on the physics that might allow it. Like life is a good example of that. It's a replicant, like DNA or whatever stores information and can be replicated.
Right.
Richard Dawkins' famous book, The Meme Lord.
The meme lord himself.
The meme lord himself. He literally coined the word
meme. Yeah, you're right.
Yeah. But he was
And
just
he's become kind of a living meme. People always are shitting on him on Twitter.
Oh, he's still on Twitter?
Yeah,
I
I mean, he
didn't know he was
barely is
still
on
around.
there. He well, you thought he died?
I thought he died.
Nah, man.
I'm about to
Come
have
on, don't put some respect on Dawkins' name, bro.
Man, I'm having a
You're thinking of Hitchens, probably.
yeah, I think I am. But I was having a what is it, Mandela effect with Richard Dawkins.
Yeah, he's on Twitter. He says something every few months.
It's like, don't forget, I invented the word meme for all of you. But the idea is that, like, something that's information replicating, and you see this example all across nature, and they argue that information is a more fundamental thing because in the universe, it's a fundamental feature, especially with binary systems that can be copied and translated, because we see it all over. Like, you have these fundamental things that just from these two counterfactuals or conditional statements or whatever replicate.
All right. So I forget what was the point again?
Yeah, just laying it out how information ties, how this abstraction of counterfactual thinking is more fundamental, and has to do with information, and then how information, how that's tied into physics.
Okay.
But yeah, they kind of delve into, and this is chapter 3 if you folks want to like really dive into this. When you get to the chapter 3, they talk about how just some really kind of esoteric stuff with like just how information is processed and discerning that. Systems with these two properties of like being able to have binary states and then also being able to be translated are called like information media. So like a good example of this is like, I think you were telling me about this. This is a kind of trivial thing, I think, for you at least, because you're like, yeah, I think we're discussing
it could be useful
this.
for the audience if you think.
Well, yeah, but one time
important
you were discussing to me, like, you're like, yeah, I can make a computer out of.
Oh, I don't think it's trivial.
You don't think it's trivial?
It took me years and
Oh,
years
okay,
to
because
understand
it's
that.
something that I never thought about, but they discuss it in the book.
I probably made it sound trivial because I was thinking of that problem for so long. It's like one of these things I dedicated a huge amount of thinking to. But no, by all means, no, it's not trivial at all. No.
Well, yeah, they bring that up, and that's something that I kind of because I had always thought about how something processes information. Because we take information for granted, right? Like, for the most part, it's kind of like.
And we're only really just starting to understand it, which is why physicists are so obsessed with it right now.
Yeah. But we do. We don't know. I mean, we see that information has this sort of. It's kind of medium independent, or it can be, like, especially because you can use something like, for instance, and how they define information as one of the properties is on-off state thing. or 1-0.
Sure.
Like you were telling me you could go on an island and use a coconut or what did
Right,
you say?
right. So you just need some way to input, you can have like I guess to really reduce it down, you need to make some kind of logical gate.
Mm-hmm.
Right. So like, of course, the classic one that we like to say, you can build any logical gate sequence if you can just create a NAND gate. And a NAND gate is just basically a not and, which means that you have two input states, right? If the two states are the same, let's say it's 1 and 1, then your output state should be a 0.
Mm-hmm.
If the two states are different, 1 and 0, then your output should be a 1.
Yeah.
And that's basically it. And 0, 0 would be also a 1 state now. So it flips that bit.
Yeah.
So if you can somehow make a NAND gate, so meaning you have just something that has two inputs and has that negation output if they're the same or, or not, whatever, then you can build a computer basically out of anything in that sense.
Yeah.
That's how people are doing things like building computers in Minecraft. They
are? I didn't know that.
Yeah, they've built their own computer in some sense in Minecraft. So you're basically building a computer inside of a computer, right?
Inception.
Yeah, so you can build a computer as long as you meet that criteria. At least, I guess, a minimum of two states and then two input states and one output state to really sum it up.
To perform a computation.
Right.
I mean, they were laying it out. This is not something that was like necessarily how things handle information, because there are physical properties. I mean, physical things are happening to compute things, right?
Yeah.
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 Like, it's fascinating. It was fascinating to me reading this because it would just, I don't know, it just kind of blew my mind. But anyway,
yeah, I guess I just want to lay out my two biggest gripes right now, I guess. But I can't really gripe too much because I didn't read the research papers, so I might have to shut the fuck up. And it's clarified in the research. But I would just say right now, with the knowledge I wish I understood more of the formalization of this theory. And then number two, I wish there was just way more examples rather than so much exposition and talking about it. And of course, I guess the third maybe would be just the words and their definitions. I don't know if I like them just yet, but my initial thoughts, I'm a little bit repelled from them. But to put it nicely. But I would really like to see formalization, a lot more examples, and then just better terminology, I guess, to sum it up.
Yeah. Yeah. I mean,
but I studied this theory too short of time to really.
Yeah. I mean,
so don't
even
take
for
my
me,
word
it's
as
gospel. This is a first run through, but it is very. Look, I found it very interesting. I like that we haven't even discussed a bunch of other stuff, but it's fine. It's like they talk about interoperability.
Right, that was another one. I was like, what?
Yeah.
I'm having real problems with the words in this. Like every time I come across a new term, they have one of their lexicon reserve words.
Yeah.
I don't understand it really very well, and I don't understand why it's necessary. Interoperability is another one of those ones where I had to reread probably 6 different times.
Yeah.
And I still don't get what it is really.
I can kind of explain it a little bit, but
should we though? I mean,
yeah. I mean, maybe we can touch on it later.
It almost seems like why introduce more?
Yeah.
More headache to the audience.
But I mean, I guess maybe we can talk about later on in future episodes, because I do really want to dissect more of this. And
yeah, it's interesting. I think if I could just read way more and maybe even translate it into a more easily understandable language,
like tying it into other. Yeah, because I think the thing is, like, the terminology is kind of, you're trying to find synonyms or things that that are sort of similar.
And sometimes when people are too in their own theories, they're in their own world of understanding. So you need another person to kind of pull them out.
Help translate
that's why I like to, like when I read a lot of things, I like to make my own version of it. Yeah. Because I know that if I can make my own version of understanding, then I can easily
synthesize it. Yeah.
I can way more convey it easier to an audience than trying to haphazardly use their words and terminology.
Yeah.
So yeah, I'd like to definitely look into this more. It seems really interesting to me. I definitely would not throw it away or like dismiss it offhand, because this is the kind of stuff we need right now, right?
Yeah.
You need new, interesting insights, real, unique ideas. I like it. I mean, I like the concept if I'm understanding it correctly. I'm just going to boil it down to formalization of thought experiments. That just sounds easier to me. Yeah, I mean, I like it.
Yeah, and I do see this kind of ties into a lot of the stuff that we've been running into, right? With, I mean, in later parts, they talk about the connection between computation and information processing or information systems, which was like just fleshed out in the 80s, you know, by like...
Oh, by Shannon and whatnot?
Well, by Shannon, and then there was also Ralph Landau, Paul Benioff, Richard Feynman, funny enough, Charles Bennett, and David Deutsch. Like this collection of individuals that just kind of helped raise questions about the connection between information and physics, you know, kind of bridged that gap a little bit.
I know the first time it really like it made a giant light bulb in my head was with Shannon.
The Shannon paper.
I was like, this is fucking genius. If you don't know, the Claude Shannon information theory paper is like, it's a work of art. So underrated. It's one of these massively underrated things where you only really figure it or learn about it, I feel like, as like a physicist or maybe even an engineer. That you're just like, how did I never hear about this before?
No, but that's kind of the interesting thing when they, I mean, we're kind of peeking behind the curtain a little bit, but there was that kind of has to do with interoperability. How information systems, they're finding that information systems are medium independent. Like it doesn't really have to do with like like the fundamental framework is medium independent. Exactly,
right? Like with Claude Shannon's paper, like he basically made a mathematical formalism for information independent of the components and things, where he would allow you to do like things like, oh, you can add in like how long it takes for a signal to transfer, like whatever, like you know, the energy loss you get from signal or whatever it is.
But you basically had StatMech come out of it, right?
Right. It was like, you have things like Shannon entropy, right?
Yeah.
It's very fundamental and abstract in its conception. But I mean, information theory, I think that, to me, that seems like one of the big, you know, papers, or I guess book, I'm not sure if it was a book or paper, that's one of the big write-ups that kind of spawned this whole information thing, at least definitely for me personally, when I started realizing, how useful and how leading edge understanding information is in terms of, you know, modern research in physics and other STEM related fields.
Yeah, this kind of pushes the dialogue too with like or drives the discourse around, do we live in a simulation kind of talk, doesn't it? Like, I mean, you see a lot of, in a lot of circles, they take this as like, oh, our universe is sort of simulated because you look at how many binary systems, like there's sort of like the universe is sort of like a computation kind of machine, right?
I don't know if I could ascertain that though.
Yeah, I mean, like, I think it's interesting. I mean, seeing analogs, right? Like,
because also our universe is fundamentally quantum, right? And what the fuck is
I mean,
that
but
about?
if quantum is like, if quantum is like, if it's from a pure, well, the electron's kind of one of the more interesting fundamental particles, but especially because it just exhibits such a unique binary state for, like, the Pauli exclusion principle, right? And then also other interesting binaries like position and momentum are
they have this link together.
They're incongruent. No, I mean, like they're damn it. How am I blanking on the term?
They have
Heisenberg-Uncertainty principle.
They're non-commutative.
Non-commutative. Thank you. Jeez, I can't even think of the word. But that's an interesting binary too. There's like a lot of interesting binary rules of, like, which are counterfactuals, which are things that you can and can't do. And then everything else falls out from.
Is that what a counterfactual is? Something you can or can't do?
Yeah.
You sure?
Yeah, I have it here in my notes.
I'm trying to understand for myself, honestly. I don't know.
Yeah. I mean, in my notes, it's an expression of what has not happened but could. It's what is possible and what isn't.
Okay, what is possible, what isn't? Or wait, what is possible, what hasn't?
And what isn't.
Oh, and what isn't?
That's a good example of that.
Okay. I'm sorry, David and Kiara. I don't know if I like it, but
why not just come up with your own word, right? Like
because counterfactual already is something, And I feel like this is
Yeah.
like slightly off from what it is.
Because
Or maybe I just don't know what
You
I'm
know
talking
why?
about.
I think it's because the etymology of the word is the same. I'm like, because I'm kind of a literal person. So
yeah, the counters. I hate the counter part.
because if you're
lot.
countering a fact,
Yeah, it's almost like.
you're saying you're negating the fact or something, right?
But and the thing is with the normal conception of counterfactual.
yeah,
It is a negated like conditional statement.
yeah,
But this one's saying what's possible and not possible.
yeah.
It's
In
almost confusing.
summary,
It's like, well, why the dichotomy? Why possible or not possible? Why not just not possible? If it's gonna be counterfactual or something. It's fucking me
Yeah.
up, man.
It is.
I need a better word or something.
or maybe
I'm just dumb and I'm missing the whole point.
No, it's
Leave a
not
comment
that.
if we're dumb and we're just missing the point, guys. Because I mean that's a very possible one. Let's
It's
be
very
real.
possible. Yeah, I mean, this was just
We did this
a quick
research.
run through.
I mean, how long have you been looking at this book? Like a couple weeks now or something?
No, this is literally like 48 hours.
Okay.
Yeah.
So you got 40 hours of like.
Of
less than 40 hours of research.
Yeah, the equivalent of I spent a whole night staying up reading about this kind of thing.
And I've got like a few hours of research, so we could definitely be the idiots in this situation. We probably are.
We probably are. It's like when you have an essay paper you have to write,
Right.
and you do it the night before. That's basically
Sometimes those are the best though.
Well, basically, I just binged the knowledge in the past 48 hours and just
Yeah.
kind of just took a lot of information in.
Right.
So, but it definitely necessitates more examples for sure of counterfact. I kind of wanted to elucidate like counterfactual thinking
Yeah.
a little bit more. I mean, in the book, she just kind of talks about.
I almost wish we could just get our definition straight before we start even expounding upon that.
Yeah, I mean, we gave the listeners I gave the listeners the definition, but I mean, I still was not happy with
But you
it.
still like that?
Huh? I
But
still like
you're
the
s-
definition.
Yeah. Because
No,
the name almost doesn't.
no, because I agree with you.
Yeah, I don't-
I'm a very literal person.
But I think
saying
that might-
counterfactual is.
But I think that might suggest that A, it's either they have a shitty word, which is possible, or B, we're missing something more fundamental to that word. Which means that we don't quite understand the definition. That's why I'm so reluctant, because I'm like, am I missing something deeper behind the meaning of counterfactual? Like, why that word? Because usually when that happens, sometimes in physics, is like I'm not getting the deeper part of that word or that message they're trying to convey.
Yeah.
And I would assume, people with the credentials of Deutsch and Chiara, I forget what's her last name, Martello.
Yes.
Marletto.
Sorry.
Marletto.
Chiara
I would
Marletto.
assume that they have a good reason to call it that.
Yeah. Yeah. I mean,
Which means that they're probably implying something deeper that we're
yeah, because I
missing.
mean, counterfactual thinking. I mean, if we're talking about, Wikipedia says counterfactual thinking is a concept in psychology that involves the human tendency to create possible alternatives to life events that have already occurred. Something that is contrary to what actually happened. Counterfactual thinking is counter to the facts. These thoughts
counter to the
consist.
facts.
These thoughts consist of the what if, and if this happened statements. It's when thinking of how things could have turned out differently.
God, I hate the word still.
It's still bad.
It still sucks, man.
It still does suck. But
'Cause
it's
like
counter
even
to
if
the,
it's it doesn't have to be
counter
counter
to
to
the
the
facts.
fact
Yeah,
all the
that's-
time.
that's the-
Like if it still happened, it doesn't have to necessarily counter the facts, right?
Yeah, this is kind of one of
It
those
sucks,
things. The
bro.
terminology
It
is not
sucks.
very good.
I think it sucks. I'm
'Cause
gonna put a stamp on the it
the
sucks.
terminology needs new branding.
Yeah.
Yeah.
It
Because
almost makes me not want to research it more just because of that. That's a bad sign, guys. I don't know if I'm gonna still put it out there that I still like the theory and everything,
Yeah.
but man, that's bugging me.
yeah, it held me up for a long time, but once they started giving examples of like, well, the counterfactual thinking is here's an example that in our framework of what it's like.
Yeah,
And
you were able to look past it and kind of just
kind
get
of
that
like
idea.
get the
Yeah,
idea
yeah.
of what they're saying. Yeah, and I mean, hey, if you're listening to this, check out the book. It's actually really good.
What's the book called? One,
It's called The Science of What Is and What Isn't.
The Science of What Is and What Isn't, and it's by
Or
Chiara.
sorry, better yet, The Science of Can and Cannot.
Yes, the right title is usually good.
Yes, The Science of Can and Cannot, A Physicist's Journey Through the Land of Counterfactuals by
And it's-
Chiara Marletto. That's ChiaraMarletto.
Gotcha.
And yeah, just you kind of just it is one of these interesting books that kind of shift. It's a shift in paradigm thinking. So
Cool.
so yeah, go ahead and check it out. We'll probably, I would love to have her on, or somebody that maybe we can get one of their grad students to come on the show.
Well, we're getting we talked to Jonathan now, and he knows Kiara, so maybe we could
does.
have something. But no promises. Just saying, we might be able to concoct something if we can.
Yeah.
You know, your boys. We try to work some magic here and there every now and
Yeah.
then. So we're gonna try. You know, we'll see.
We'll see.
We'll see.
We'll
No
see, but
promises though.
That would be fun.
Just we'll see.
But let's see in the comments below what you guys think. You know, make sure to like, comment, share, subscribe if you liked this episode and what we did here. This was kind of one of those what's some of the people that literally ask for us to be like, no, we love it when you guys flesh it out.
Oh yeah.
Yeah, this is one of those.
Yeah, it is.
Yeah.
This is one of these.
We're
figuring it out.
We're figuring it out.
Fly. But yeah, if you guys enjoyed it, guys, you know, of course, check us out, eigenbros.com,
Yeah.
Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then, of course, the Patreon. You know, you guys have supported us.
Oh,
You've
yeah.
been continuing to support us. We greatly appreciate it, guys. We couldn't do without you. So patreon.com/Eigenbros. Check it out if you want to help us out, support the channel. And I think that's it.
I think that's it, folks. We'll see you next week.
All right, guys.
Peace.
Ta-ta.